Hi, I'm Will, and here's my Physics Lab 1. So the objective of this lab is to observe and model an object moving at a constant speed, and then to graph and compare the observations against the model. And I also use Newton's second law to explain the observation, as well as create the model itself. So next, here is my observation. So as you can see, it's a ping pong ball rolling across the table. The system in this situation is the ball itself, where the surroundings would be the air that it pushes through, and then the mat that it's rolling across. Um, I set the origin of this experiment to be on the ball itself, in the very center of the ball when the video starts, and because of that, the ball is moving in a negative y direction. I only focused on the y-axis movement because there was a little bit of change in the direction on the x-axis due to the ball being a perfect sphere, and the experiment called for constant velocity with no change in direction. From the observations, I know that finding the initial velocity is essential to making an accurate model. And knowing that the velocity is constant throughout the captured moment and that the velocity is the derivative of the position, I was able to use the tracker to determine the approximate slope of the position time graph. And this is my approximate velocity for my model. I know that the velocity is constant because the position time graph is almost entirely linear, meaning that there is little to no acceleration and that the ball is not moving any faster or slower than it did at a previous time. Now that I had my velocity, I had just about everything I needed to create my model. In order to do this, I would be using Newton's second law, which at its most basic form is force equals mass times acceleration. And after some algebra, it becomes our velocity update formula. And then using the velocity update formula, we can come to our position update formula. I didn't really need to use the force equals mass times acceleration because, as I showed earlier, there was no acceleration, which would mean there was no net force, which is essential to an object moving at a constant velocity. And then as far as the velocity update formula goes, if there's no net force, then we know that the final velocity will remain the same within each update, which once again is accurately portrayed in our observations, which leaves us with the position update, which was about the only thing that changed through our observation, where the ball was actually moving in a negative direction. Um, and because of this, it's essential for our model that we really focus on the position update formula. Once again, to reiterate, we can tell there was no acceleration through our observation because the position time graph was almost completely linear. Next, I wanted to create my model itself in GlowScript. So the changes I made in GlowScript essentially reflect the formulas displayed on the previous slide with a few added extras. So first of all, I inserted the mass of the ping pong ball under the system mass as well as its initial position, which would be set under initial conditions. As I mentioned earlier, the initial position of the ball was set on the center of the ball itself, meaning that it's all zeros. And then there's also the initial velocity of the ball, which I found using the slope of the position time graph. Um, and then next, I applied the velocity update formula and the position update formula in their respective areas. It's important to note that the velocity is constant, so the formula doesn't do anything for velocity update, but I still thought it would be important to include in case I wanted to model something with a net force that was other than zero. So my observation versus model graph is displayed here. As you can see, they differ very slightly. There's a few reasons which may have caused slight deviation. The first of which is that we're generalizing when we say velocity is constant, and because the experiment didn't take place in a vacuum and there was friction between the ball and the surface of the mat, the ball is technically slowing down. However, that would on the graph that would show that the model is beginning to go above the observation, which isn't the case. So it's most likely that human error is the main culprit, and that using tracker, it was a bit hard to find the exact center of the ball within every frame, which kind of led to slight deviation. And finally, I wanted to go over the extra questions posed. The first of which is what would happen if the axis was flipped. In my situation, the ball is moving in the negative y direction, so if the axis were flipped, it would now be moving in the positive y direction, and I'll have to account for this by changing its initial velocity in my model to move in the positive direction. What are the forces acting on the object that bring its net force to zero? In this situation, it would be the initial push of the ball moving against the air resistance and the friction between the ball and the mat. And altogether, because as we showed earlier, there was no acceleration and therefore no net force, we can conclude that the friction and the air resistance and the initial push all essentially equaled each other out. Thank you.